Welcome to the fifth of 14 videos on the arc flash truth no one explains. My name is Joe Chacon. I'm the president of Podge LLC and Chacon Engineering. I'm a licensed professional engineer in multiple states and have been an electrical engineer for almost 30 years. Please like and subscribe as this helps us get this important information in front of more people. This video is going to talk about the effects of bus gap and enclosure size on incident energy. Table 8 from the IEEE 1584 standard shows typical bus gaps and enclosure sizes. I like to get cut sheets or measure these myself for accuracy purposes. When prohibited, I do defer to Table 8. I also like to see the equipment to evaluate the efficacy of the equipment. My purpose in this video is to show you the importance of knowing your bus gap, sometimes called electro gap, and also the importance of enclosure size. There is an unghastly amount of math to do this, and I will get into that in video 7, just not this one. There are a couple of competing things going on with bus gap. The first is Paschen's law. Basically, we want our bus bars to be separated far apart because that reduces the likelihood of a breakdown. However, when that breakdown occurs, the incident energy equations show it actually increases. Look at the equation for incident energy. The takeaway here is you want to be accurate with your bus bar gap in your model. I took the liberty of plotting incident energy as a function of bus gap for a vertical bus bar arrangement in an enclosure 508 millimeters by 508 millimeters by 508 millimeters with a working distance of 18 inches, bolted fault current of 60 kA or 60,000 amp, and voltage of 690 volts. Notice the incident energy rises from about 20 calories per centimeter squared for a 3/4 inch gap up to 36 calories per centimeter squared for a 10-inch gap. As an electrical engineer, I'd still rather have that larger gap spacing. Now, let's take a look at how enclosure size affects the incident energy. The standard emphasizes a correction factor called equivalent enclosure size, or EES. It is simply the height plus the width divided by 2. Then, correction factors are applied to that according to a second-order polynomial fit based on whether the enclosure is defined as typical or shallow. Shallow is always applicable to low voltage and means one of two things. The depth is less than 8 inches, or the height and width are less than 20 inches. The standard also has some particular rules that force us to use if-then logic based off the enclosure width and height. That comes from Table 6 in the standard. Let's look at the same example from before, where we looked at incident energy as a function of bus gap. Let's fix bus gap at 25 millimeters. The rest of the same parameters are used, but now we're looking at incident energy as a function of the area of the opening of the enclosure. Okay? Notice it starts at 21 calories per centimeter squared for a very narrow opening and goes to 16 calories per centimeter squared for a very large opening. The conditional logic of the equivalent enclosure size and the corresponding correction factor can be quite intense. So I've made a graphic from MATLAB to visualize it better. The plot is true width in inches and true height in inches on the X and Y axis respectively. The Z axis is the equivalent enclosure size in inches. Notice the conditional logic that drives the EES, or equivalent enclosure size. The big idea is to collapse the complex, nonlinear effects of enclosure geometry on arc energy reflection and confinement into a single normalized parameter that allows consistent, experimentally based incident energy predictions across vastly different enclosure sizes. So, we've gotten into the math a little, just showing the importance of documenting bus gap, separation, and enclosure size. We'll get into an actual example calculation in future video 7, where I'll take you through all the details of the equation. The next video will look at bus bar configurations and how they can vastly affect incident energy.